right. I'd like to thank the vBrownBag folks for inviting me to talk this first day of VMworld about virtualizing high-performance computing as a service. My name is Andrew Nelson, and I work in VMware's Office of the CTO, which was a recent change for me. For 4 years, I worked in VMware Field Organization as a specialist for the Western US, focusing on big data, HPC systems for customers. I presented last year at VMworld with UC San Francisco on virtualizing their genomic pipelines. And before I was in the VMware field, I was a consulting architect for various federal and military agencies, and I got my VCDX certification when I was the lead virtualization architect for the US Marine Corps. Now, when you think about high-performance computing, you're probably already thinking of very specialized hardware and software that's geared towards very specific use cases. This is your typical climate modeling, earthquake prediction, which would be nice, as well as oil and gas mining, mechanicals and material science. But to expand that definition of what we think of as e-commerce, script analysis, big data, stream processing now, all of these things generate a large amount of CPU and memory activity, as well as I/O activity, and typically you're in an environment where you will never have enough hardware to solve the problems all at the same time. So, why bother virtualizing high-performance computing? Why don't we just do bare metal as a service? And so, case in point, if you look at traditional supercomputing facilities, they're extremely limited in what they're allowed to offer from a capability standpoint. And instead of any flexibility whatsoever, researchers don't have root access. They don't have the capability of picking their Linux distribution. Maybe it's a customized Linux distro just for that particular facility. On the slide here is an image of the Titan supercomputer, which is actually rated at around 27 petaflops. This is at Oak Ridge National Laboratory. And I bring that up because late last year, a geophysics researcher from the San Diego supercomputing facility actually had time to run on Titan an earthquake modeling and prediction code that he had optimized very heavily over 3 months of time with himself and various computer science staff at the Oak Ridge National Labs. And even though it's rated at 27 petaflops, after all of that optimization, they only used around a peak of 2.7 petaflops for that code. Now, the interesting part that they found out was that they actually correctly predicted that the Puente Hills fault would be more seismically active, and was confirmed very early this year, as opposed to the more popular San Andreas fault. But what is the possibility with putting this onto any sort of cloud environment is taking the ability to bring their own workload to any generic environment and be a lot more flexible about the requirements, spend more time focusing on their codes than really trying to customize it to run on a specific platform. And researchers, research computing scientists, are caught in a very quick cycle of experiment, prototype, and scale. And to be able to do this very quickly with flexibility is what they're looking to do with virtualizing high-performance computing. So what do we know today about virtualizing HPC workloads? As I've done with genome pipelines, with big data, if you can think of throughput computing as another name, which is embarrassingly parallel algorithms, anytime you can divide up a problem into 1,000 different pieces, and all of those can execute simultaneously before you feed those results back, virtualization handles extremely well, and we can get very close to bare metal performance just on any generic hardware platform. And we can share it because the assumption is that these jobs are 100% utilization all the time. And the reality is that researchers on an experiment prototype and scale methodology are very quickly trying to run small jobs, lots of small jobs, thousands of these per day actually, as opposed to maybe one large job which is taking up a multi-petaflop range over time, which may be in the occurrence of once a month versus many small jobs typically on a daily basis, where virtualizing HPC actually works fairly well. And if we need to do even better, if we need to slice off the last few percent latency, if we need to use VM Direct Path I/O, if we need to use certain devices in a PCI slot, we can get bare metal performance with VM Direct Path, as well as with SR-IOV support. Of course, if we use those, then we lose the capability of vMotioning those workloads around, so we lose some of that flexibility. And so some of the work that still needs to happen here, and definitely if you want to hear about what the Office of the CTO at VMware is doing around this, we're at the CTO booth in the Solutions Exchange. We're behind. We have high-performance computing poster up talking about some of the latest benchmarks that we've done on these platforms. But if you have a tightly coupled workloads, if you're using something that's leveraging MPI, message passing interface, that's trading very small messages in a nanosecond kind of latency, then that's when you will have higher performance hit than just the generic throughput workload. So those are some things to watch out for, as well as some of the projects I'm engaged in personally is working on creation of flexible cookbooks. Again, pick your poison, whether you're working with whatever configuration management system to deliver those for traditional HPC schedulers, and bridging that gap is in the vein of big data extensions to allow easy accessibility for easy prototyping and setting up these systems with self-service access to the users. And finally, enabling vMotion from some of these other hardware products like Mellanox, Intel, something doing RDMA, as well as enabling GPUs with vMotion. And today there is no Xeon Phi support in a virtualized environment. Now finally, some things to check out quickly. Of course, we have to pay attention to hardware. This is high-performance computing and how we enable that for the users. And definitely check out the high or the low latency white paper. Should be the first thing that comes up if you do a Google search. You'll need to learn some sort of configuration management tool, because all the time you're going to be setting up master nodes for individual grid clusters and many slave nodes. So make sure that these are all ready for that rapid prototyping stage. And finally, get ready to coordinate these with your provisioning layer, because your scheduling of jobs and resources, VMs, all of that is happening independently of your provisioning layer, and learning how to orchestrate and coordinate the two of those is key to actually making this a self-serve environment, low touch for your users. Finally, definitely check out the booth. I'll be presenting in just a very few minutes. That time was changed, so I'll be running over to Moscone West to talk about virtualizing Hadoop on vSphere with Adobe. The talk on Tuesday is with Edmund Dimitia from the Johns Hopkins lab that's virtualizing nuclear dynamics codes. So very interesting talk. It was sold out, so hopefully there'll be another time available, as well as business focus side with Josh Simons, who's head of HPC in the Office of the CTO, and Matt Herreras, director of SCs for their SLED accounts at VMware. And finally, if you want to know what we're doing in the latest low latency network function virtualization, this is with Bhavesh Davda on Wednesday morning. And again, thanks to vBrownBag for giving me this time to talk about virtualizing HPC, and hope to see you around VMworld.